So, in the last session we saw that we have devised a set of list manipulating operators. We have looked at a set of list manipulating operators which are given to us by many programming languages, and we can easily translate an algorithm written with those algorithms to a programming language. So, let us look at our first deterministic algorithm. This algorithm is called depth first search, and the algorithm is similar to what we wrote earlier, except that everything is frozen. There are no non-deterministic choices here. As before, the algorithm maintains two lists and it maintains two lists of pairs. So, both open and close, they will contain node pairs. So, just to remind you, node pairs are pairs where you have current node and parent node, and we start with creating the first node pair. The first node pair that is available to us is the start node. So, if you look at the state space, then this would be a start node and it would have some children and so on and so forth. But since this is a start node, we assume that it has no parent, and in fact, the algorithm for reconstructing the path will terminate when we reach the start node, because we will identify the start node by a node which does not have a parent. The name S is not meaningful, as you know, in programming languages you can give a name to any name to anything, it is a meaning that is important, and in our case the start node will be identified by a node which has null as a parent node. Now, remember that this is a list, this thing is a list where the head is this node pair which is S comma null, and the tail is an empty list, because we have not yet started exploring nothing. So, what would happen is that once we explore the space, then we would generate its children and then we would add these two open. So, this will go into open, 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 and this will go into close. We will often denote close by double circles essentially. But initially, as you can see, close is an empty list, because we have not seen any nodes here. So, remember that the algorithm simply says generate and test, pick a node, test whether it is a goal or not. If it is not the goal, add its children to open essentially. So, we will start off initially in open we have only S. So, when we say, when we extract that node, we will get the node initially, we will get this S comma null, and this S is referred to by this variable n. So, in this name n is the name of the variable that we are always picking for inspection in the node nodes. In the first instance it would be S, in the second instance, for example, if we pick this node A, it would be A, in the third instance it might be B, in the fourth instance it might be D, C and D and so on. So, whichever is the node, we will refer to that as n, and like we discussed in the last class, this is the first element of a pair, and we are not really particularly bothered about the parent at this stage. We would be interested in the parent only when we want to reconstruct the path to the this thing. So, we are interested in this node n, and we can access it as the first element of this pair which we extract from open, and we always, as we said earlier, we always take the first node in open, and that is the head of the list, and that is the easiest to extract essentially. Okay. So, we take this node n and we apply the goal test function. As before, we have done this in the non-deterministic case, but let us also go over this algorithm again essentially. So, this statement says that this is true, goal test n is true. So, goal test is a function which tells you whether you are at the goal node or not, and it returns in terms of functional programming languages either true or false, and if it returns true, then we are done, and we will just call the function reconstruct path that we will see in the following slides. And to call this function reconstruct path, we give as input the node pair that we have just extracted, of which the first element was the goal, and whatever is enclosed which contains records of everybody's parents essentially, right. Every node that we have seen and its parents. So, if it is not the goal node, so if goal test is true, then we construct the path. If it is not the goal, then the first thing we do is we add this node pair to closed, because it may be leading to the eventual goal and we want to be able to trace the path back, and we can add it to closed node simply as at the head using the same dot operator. Then we call the move gen function which the user has given us, which gives us the neighbors. So, this is n and you get the neighbors of this thing, and this is what move gen returns to us, and we call this set of nodes that this returns as children. From this set of children, so these nodes, we will remove any node which is already on open and already on closed. So, we have seen earlier the impact of removing these nodes is that you do not want to keep visiting the same node again and again. It only increases the search effort, and you can often get away by simply not looking at those nodes again. So, there is a function that we will write and we will do it in the next few slides, which is called the remove scene function, and what this function does is that it takes these children which are generated by move gen function and removes any children which are either already on open or already on closed essentially. And so, now we may have some number of neighbors, and but these neighbors are just the nodes that are the neighbors. Our search algorithm wants node pairs, and we have this last small function that we will write, which will actually construct the new node pairs. So, it will take these new nodes which we got after removing all the duplicates, and to this new nodes, for every node in the new node we will keep n as a parent, because all these were children of n essentially. And having constructed this new pairs, we will simply add new pairs to the head of this thing. So, we will append these new pairs at the beginning of the new open. Why do we use tail open? Because we have not explicitly removed that node pair from open. So, we just implicitly say we will work with the tail, and then these new things will be added at the head. So, when we add this at the head of open, then we are treating open as a stack essentially, because this is like a stack, and the properties of the stack, if you remember, are last in, first out, and the latest nodes that are generated, they would be inspected first, and we will look at this how this behaves in a little bit later. So, let us now fill in the functions that we talked about, the reconstruct path function, the remove scene function, the make pairs function, and so on. And if you do that, then the algorithm would be complete. Okay. So, first let us focus on the remove duplicates function. So, what is the task? That we are given to us a node list. What is this node list? These are children of or neighbors of n, and from this we want to remove anything which already occurs in open or closed. Now, remember that open and closed are both made up of node pairs. So, every node in open and every node in closed is a pair, and we will need to look inside that pair to check whether any of these children are present in that or not. So, here is a simple algorithm which does this. It is a recursive algorithm, and like any recursive algorithm, we first look at a base clause, and the base clause is that the node list is empty. If it is empty, we have nothing to do, we just return the list essentially. Otherwise, we take the head of the node list and we call it node. We assume that we will write a function called occurs in, which will look at whether this node, which is the head of open that we just extracted, occurs in open or not. And likewise, we will use the same function occurs in to see whether this node occurs in closed or not essentially. So, if either of them is true, if the node occurs in open or the node occurs in closed, then we do not want to add it. So, what we return is simply remove scene applied to tail of the node list essentially. So, that means we have taken out the first element, inspected, checked whether it is there in open or closed or not, and if it is not or if it is either in open or in closed, then we just discard it and work with the rest of the list. If it does not occur, which is when we come here to the else clause, then we add this node to whatever we get by processing the tail of the node list and applying the remove scene function to the tail of the node list. So, in that manner, in recursive manner, we go over this node list one by one, keep checking whether it is in open or closed or not. That checking is done by this function called occurs in, which we will see, and eventually remove anything which occurs in either open or in closed. So, what is this function occurs in that we talked about? What this occurs in needs to do is to take a node as an input and a list of node pairs. Remember, both open and closed are lists of node pairs, and tell you whether this node occurs inside there or not. So, if the node pairs is empty, that means we have finished inspecting all the things, we just simply return false. Else, we look at the first node, and if this node that we are interested in is equal to the first node of the head of the node pairs. So, this head will give you the first node pair, and this first will give you the first of this. Okay, so, the head takes out the first node pair, and this first looks at the first element of that, and if that element is equal to node, then we can return true that yes, it occurs in that node list that we are looking at. If it does not, then we look into the rest of the node pairs, which is given by the tail of the node pairs, and we use the same occurs in function to check for that. Eventually, it will finish looking at all the node pairs, and it will come back to the base clause, which is says that if there are no more node pairs, then the node does not occur inside that. So, remember that once we have removed the duplicates, we want to make pairs. Why do we want to make pairs? Because our search algorithm denotes everything, keeps everything as a pair essentially. So, every pair is a current node and its parent node, and we simply want this function to do that essentially. So, what is node list? Node list is a set of children of node n, the parent of all these nodes is n, and for every, and from these children we have already removed the duplicates, which will. So, if you go back to the algorithm and see, first we extracted children here in line number 9, then in line number 10 we removed everything that is there, and now we are focusing on line number 11, which says that you need to make these new pairs essentially, and that is a function we are looking at, and that function we will call as make pairs. And the make pair is as follows, that if this node list is empty, then we are done, essentially we do not need to make any more pairs, and therefore, we can return the empty list. Else, what we do is we take the head of the node list, which will be an element, which will be a node, which will be a state in the state space, and the parent of course, we have n, and we make a pair out of this. This pair is made by using these brackets here, and we add that to the head. Remember, this is a dot operator, which makes a list, which distinguishes the head and the tail of the list, and we do the same thing for the tail of the node list. Okay. So, recursively we traverse down the node list, constructing the node pair one by one essentially. So, for example, if the call to make pairs is with a list containing A, B, C, D, and the other list is S. So, remember that this is what we had said, that if you are doing with a start node, then you have A as a child, B as a child, C as a child, D as a child. So, we have these 4 children which are A, B, C, D, and then we have the parent S. What we want to do is to construct a list of pairs here, where every element A, B, C, D is there along with S, which is the parent of all these nodes, as you can see from this diagram. So, the function make pairs does that for us. When we reach the goal node, we want to reconstruct the path. So, we have seen earlier that the path can be reconstructed by, because when we reach the goal node, we will call it at the point when we are looking at a pair which is called G comma X or something, where G is the goal. So, once we find the goal node, we will say okay, let us trace back the path. We know that the parent of G is X, but what is the parent of X, that we have to go into the closed list to see, and therefore, the reconstruct path. So, this is the node pair that will be input to this reconstruct path function, and the other thing would be input is the closed list, and the closed list will have somewhere in it a pair which says X and the parent of X, and let us say the parent of X is Y, and then somewhere it will have a list pair containing Y and the parent of Y, and so on and so forth till we reach the start node whose parent is null. So, let us see how we can do that. So, essentially we are tracing back the path through parent links, and parent links are kind of implicitly stored in the closed list. So, let us look at this function. We want to go to that node in this list of node pairs which is enclosed. It says that the parent that we are interested in is the first of the head of the pairs. So, we look at the head of the node pairs, and if the first element is equal to the parent, then we say yes, this is a node pairs that we are returning it, else we move to the tail of the node pairs essentially. So, essentially we are scanning through the closed list, looking at one element at a time and seeing whether the parent that we are interested in, which is this node X here, is present there or not. So, once we find that X, then we will look for the parent of X and so on. Okay. So, what do we have? We have node parent as a node pair as input, and the path that we start with is the node followed by tail essentially. What does this translate to? If you look at the example here, when we have terminated with G comma X, then the path will look like a list which contains only G, which is equivalent to saying G comma the empty list essentially. And then when we find the parent of G, we will put it here, and then so on and so forth essentially. Of course, this we do not need. So, first so essentially we are saying that we start off initializing the path to node followed by this thing, which is this empty list, and then when we find the parent of G, we will add it, and then the parent of X we will add before that, and so on. So, we will essentially eventually have a path which goes from S to G and so on essentially. So, while the parent is non null, remember that this will be null only when we have reached the start node. We add the parent to the path. So, what does this mean here? So, now our list will look like X comma G, where X is the parent and the path was originally just G. So, we add that to the head of this thing, and then look for where X occurs using this skip to function that we just wrote, and then keep repeating this process till we reach the null node. When it is when it reaches when the parent becomes null, we know that we have found the path, and then we can return the path essentially. So, that is a function set of functions that we have used in depth first search. So, now we have a complete and detailed description of the algorithm depth first search. Let us look at a variation of depth first search, which is where we treat open as a queue as opposed to a stack. When we talked about depth first search, we said open is like a stack, and the stack has a property that the last nodes to go in are the first ones to come out of open. So, LIFO property, and in some sense you look at the most recent nodes first essentially. When we treat open as a queue, the queue has a property of first in first out, which means that the first nodes to go in are the first ones to come out. So, if you just look at the example that we have been talking about, if we have S and A and B and C and D. So, when we have put S into closed and A, B, C, D are in open, the head of open is always A. So, we will always put A into closed and we will generate the children of A, let them be E and F, let us say. Now, the question is, after we have inspected A, which is the next node that we should inspect it. Now, if you remember how depth first search works, it says the newest nodes first, or the last nodes which were inserted into open first. So, that was last in first out. So, the last in first out would be picking the node E, but first in first out would pick the node B, because this nodes E and F would have gone to the end of the queue, and this is doing this treating open as a queue essentially. So, depth first search would pick E and breadth first search would pick F. We will look at the behavior of this algorithm in a little bit more detail. The two will do a comparison of which one seems to be better, but the fundamental difference between the two algorithms, depth first search and breadth first search, is only this. So, all this code that you see here is identical to what it was in depth first search. The only difference is in line number 12, and in line number 12 we have appended tail of open to the new pairs that we found. In depth first search, new pairs came before and the tail of open came later. In breadth first search, tail of open comes first and the new pairs go later, and that is why it behaves like a queue essentially. At this point, we can also observe that because depth first search chose E and F, what this does is deepest nodes first, and that is why, as you can guess, it is called depth first search, whereas what FIFO does is shallowest nodes first, or you might say closest to start. We will see in the next few slides that the consequence of following the shallowest nodes first will be that breadth first search will always give us the shortest path. So, as you can see from this very quick comparison of the two algorithms, depth first search is like an impetuous search algorithm. It just runs off in some direction and will backtrack only if it reaches a dead end in that direction. Remember that if for example, E and F were to be dead ends, then it would remove them from open and add nothing to open. So, eventually it will go to B and so on. So, that is equivalent to saying that it has backtracking and so on. Breadth first search on the other hand is very conservative in the sense that it never strays far away from the start source node or the start node and stays at as close to the source as possible essentially. So, let us look at some of these properties in a little bit more detail. So, what we just discussed here is that this is the open list that we have, it is ordered from left to right. We extract the first element from open from the head of the list, from head of the open, and then we call the moveGen function, which gives us a list of new nodes. And what DFS does is that it adds them to the head of open, and what BFS does that it adds them to the tail of open. So, open is like a queue for breadth first search and open is like a stack for depth first search, and consequently the behavior, and by behavior we mean in what order does the search algorithm explore the space, is radically different essentially. If you look at depth first search, then you can see from this diagram that it is gone off in some direction. So, it came down this path and then when it reached a dead end, it backtracked one level, tried another path, then again dived into some path, then again reached a dead end. So, again it backtracked and again it tried different paths. So, it keeps doing that. It keeps going away from the source node as far as possible, and only when it hits the boundary it backtracks and tries some other path, and in this particular thing presumably the search algorithm would be like this. Now, notice that this was the start node and this is the goal node, and this algorithm has no clue as to where the goal node. Eventually, of course, it will hit the goal node because the state space is finite, and it will inspect every node one by one, because in every cycle of the algorithm it takes one node from open and adds it to closed. So, if there are a finite number of nodes, it will eventually reach the goal node, but the path that it finds may not be the optimal one, and that we will see. Breadth first search, on the other hand, as I said, tends to say close to the goal. So, this was the start node and then it just goes trying to stay as close to start as possible, and then of course, eventually it will read this thing. See, as human beings, if you were to think of this as a city map, of course, we have not drawn the roads, but you can imagine the roads here, and every node is a junction of roads. As human beings, we could say, okay, we have a global picture, and it would be nice if the algorithm search were to head in this direction somehow and not go all over the place, or in this case also not stick close to home, but it would be nice if it were to go in that direction. We will make this attempt later after we are done with these basic search algorithms, and those algorithms we will call as heuristic search algorithms.